Hello, my name is Heinrich. I have been talking about statistics for engineers for a long time. And today I want to share with you my opinionated take on SLOs and how to do it. Before we dive into the mathematical aspect of SLOs, I want to highlight the goal setting of SLOs. So what are they and what are we trying to do with them? And fundamentally, I think SLOs are about engineering management and steering engineering investments with data. So we want to know, should we implement reliability patterns, should we increase resources on a certain service, and so on. And instead of focusing at the tactical aspects, when do we alert, how do we observe the systems, we are here with the SLOs going one step back and think about longer time ranges and understanding, should we spend engineering time on reliability or not. So if we are successful with SLOs, we should be able to do it. And thinking about SRE as a profession and how we steer reliability, I think we are always navigating this triangle, which is basically saying reliability is the property of the system we want to optimize or that is important for us. But we also want to keep to be productive, and we want to keep our on-call teams healthy. So we always have to balance between those three. And everything that we do, like improving alerting rules or testing systems or increasing resources on databases, these are all always trade-offs that we make within this triangle. Now, for you and your team to understand where you stand, SLOs are a wonderful tool because they allow you to explicitly manage, understand where you are and manage where you want to be. If you use SLOs for steering decisions, you're basically trading off between reliability and productivity, just your focus on features versus reliability. If you use SLOs for deployment gating, you also make very directly a productivity trade-off. And lastly, we will see also in this presentation that you can use it also for alerting, which is trading off reliability against the on-call health. Okay, now that we have the goal setting out of the way, let's look at the definitions. And this is already something that is a little bit controversial, or at least here's my take on it. There are different versions of that around. So SLI, for me, again, it's basically a management KPI. So we want to use it to steer management decisions. And management KPIs have two properties. They are moving slow, so usually a 4-week time horizon, and they are usually proxies. So you never expect to being able to measure exactly user behavior or measure exactly the performance of a certain feature. You are only able to measure proxies, like how many users used your tool, not really how happy they were and which struggles they had. So we always have to make some compromises, but important is that we have a correlation and it kind of gives us a direction. Now, an SLO is basically a threshold on an SLI. So again, SLI is a reliability KPI, and I should probably just read the definition here to make it completely clear. So this is a KPI which is calibrated between 0 and 1. So 0 means unreliable, 1 means fully reliable, and again, it measures the reliability of a service. Now, reliability objective, we all understand 100% reliability is just too expensive. We want to make a trade-off, and we have to have business and customer representatives in the room to make this trade-off effectively. And the objective is a quantitative artifact that comes out of this conversation, basically saying, here I draw a line and say, this is acceptable, this is not acceptable, and we strive to have a certain level of reliability and not more. So relatively simple, very simple, I would say, and very general terms. Now, how are SLIs and SLOs typically implemented? And almost all of them are actually formulated in this kind of long-term average success rate. So we're looking at certain population of total events, can be HTTP requests or something else, and a part of that were good events, so things where we said, okay, this was actually a successful interaction, and there were bad events which we say, okay, those were not satisfactory, and we are expressing that average or computing that average, and this will be our SLI. So if you only had good events, it will be 1, and if you only had bad events, then it will be 0. So it fulfills these properties. If you're starting your SLO journey, then availability SLIs are really the thing that you want to focus on, and this takes you a very, very long way. And here are like my top 3 ways on how to do them in order of quality. And in many cases, you can relatively quickly set some synthetic probing up. Classical example is pingdom or just pinging your host to see if it's like physically available on the internet. You can do that every minute, and then you kind of take the success rate of that operation over 4 weeks, where here the total number of probe runs is like 40,000 or something over the full month, and here you're counting your successful probe runs. The next better version of that is if you have a server backend that is powering your website, you can just count the number of successful operations on the server, and that will give you a measure for good events. And then you divide by the total number of requests that you got. So also very simple. The problem with that is that this is actually the view from inside your application, and can be that it's actually quite different from the experience that your users have. So typically, if you have firewalls or proxy servers in the middle, you are absolutely blind to every degradation that happens there, or even on the browser or the mobile client that your users are using. So if you can put the measurement closer to the users, you will get a higher quality SLI. And that is kind of the third best version of SLI that I regularly work with. Here's another type of SLI that's also quite usual. I call them latency SLIs, and if you have seen any of my talks, I always have a bit of histograms in there. Just a shout out, this kind of measurements is aided by histograms quite nicely because they are about aggregating latency over long time periods. So for this SLIs, we are asking ourselves how many operations were fast enough. And it could be just website requests, it could be ETL jobs, or it could be job executions like a cron or a job scheduling system. And we basically want to know how fast they were, and we can encode the quality of service we are providing in this kind of SLIs, a very similar way. Okay, so let's come back to this formula that we saw before already, which is how we are formulating most of the SLIs. And if we are removing this bit about the 4 weeks here, this is actually a very familiar formula. So it's just like good events over total events, say, measured over a minute. So this is what we would call a success rate, or 1 minus that would be the error rate. So it would be bad events over total events. And how does that look like? So here's the data set. I will use an example for this talk, which has some requests that we're getting in, and in red I marked the errors that we got. And here are some organic error rates, which manifested a little sprinkling on the top. And I also have injected actually 2 larger outages. Both have a 98% error rate, so almost complete outages. One was in a low traffic situation, one was in a high traffic situation. So basically the second chart is showing you how this looks like. So just good events over total events would be the green area here. Now, how does the 4-week version look like? So this event is just, this graph is just showing you that. So talking about total events over a moving window of 4 weeks, and then here the divided by the good events and the bad events divided by the total number. So this kind of request rates. And you see they look a little bit similar, maybe not too much, but you see artifacts of these red lines still lurking around. And I want to show to you how those bits are related. And let me just share my screen here real quick. So here's an animation of how the one relates to the other. So here for every frame, I'm incrementing the range of aggregation. So we are now at 10, 11 days. And every, the graph on top just shows you the total events that were good and bad aggregated over this time periods, over longer and longer rolling windows. And below here we see the average. And we kind of see how the red thing smooshes out over longer time periods and becomes a very, very thin strip. And we see also that this degradation is leaving a lot less volume behind when it's being smushed out. So that corresponds to the fact that we had here very few requests that were actually failing, although the rate was high. But here you see just very little requests after we are averaging. And here we actually have a lot of things that were failing in that time period, and it's very visible even on the 4-week scale, like 24, like 28 days here. We retain a little bit of that. So moving back to this, this here down is actually precisely the SLI. This is the green area is the good events over the total events, averaged over 4 weeks, a rolling 4-week time window. And yeah, the thing you note immediately is all the values are pretty cramped up at the 100%, right? So SLO, this is a very low SLO of just 90%. It's already like very high up here, and your SLI may be at 98%. So we are like focused on this higher end of the scale for all the measurements that we are like taking here. And although this graph was like maybe a little bit naive, you can easily do it better. This is still a phenomenon that we see quite a bit. So everything is kind of cramped up here near the 100%. So how can we visualize this? How can we do better? And there are two ways. One of them is to use the 9 scale, and you're probably all familiar with it. You say like if a 4 nines SLO, a 5 nines SLO, and yeah, it's just a convenient scale to use for these values. I put the formula in here, so it's minus log 10 of 1 minus SLI. That's what you need to put in Grafana or your tool to get this, yeah, convert from a number to like its numbers of 9s. So this will spit out 1 if you put in 90%, or 2 if you put in 99%, and yeah, 5 if you put in 99.999. And for values in between, it will interpolate. So if you put it in Grafana, you usually want to clamp this at like 5 or 6 nines, because yeah, realistically, your reliability will actually be in that range. And if you, for some reason, are getting close to 100%, this will just like run away and into infinity and not be very useful for visualizing. But yeah, again, clamped at 6 or 5 or 6 nines, this actually makes a decent gauge or a decent line chart, which is plotted here. So again, we see the request rates, the error rates as before, and here we see this has kind of 2.5 nines, and after the second outage goes down to 1.5 nines. So not very reliable experience that we are giving our users here. The next best idea you can come up with is just a linear rescale, and this is fundamentally what the error budget is. So I have the formula or the requirements basically written here. So 100% reliability should be error budget 100%, so exactly the same. And then we say error budget 0% should actually mean we are at the SLO value. So going back to here, it means the SLO value maps to 0% error rate, and we linearly interpolate between those two values. So if we are plotting this range, then the SLI will actually, yeah, cover a meaningful scale for us, and not be cramped at like a very, very small bit. And if you work out the math, there is a simple formula how you can derive it. And if you put in this formula for this event-based SLOs that we looked before, you will actually understand why this is called an error budget. And it turns out that what you end up with is just the difference of acceptable bad events. So say we have a 99% SLO, so 1 minus SLO is 1%. Total events over 4 weeks, in this case, maybe 100,000 or something. So you had 1% of 100,000, 1,000 events that are like accepted to be bad, and then you subtract the bad events that you already accumulated over the past 4 weeks. So this gives you kind of like how many acceptable bad events you have still left, and then you normalize it by the total number of acceptable bad events over the period to normalize the scale between 0 and 1. So a very natural scale, and something you may just come up with if you hear like error budget, what should that be? So here I plotted the error budget. So you see this graph is no longer like clamped at 100%. It is moving meaningfully, and you also see 0% is again representing the SLO. So here we see we breached it. Yeah, I put this kind of area on top of the error budget in red to remind you that it's actually just this rescaling of the error graph as we saw in the error rate graph as we saw in the animation. Yeah, and once we have that, so that's actually a fairly useful visualization of an SLO, we can start managing. And managing always means mapping something to a traffic light symbol. So managers only think in very, very simple terms. hopefully like simplified in a meaningful way. And here actually we have a pretty solid and proven way to simplify reliability. So if we have more than 20% error budget, we say proceed as usual, no need for special investments. If you are below 20%, we probably want to say, okay, be careful with your deployments, think about implementing more post-mortem action items, make your service reliability. You are like on the edge. And if you're red, that means your reliability has not been acceptable. You have been down too much. We have not been performing well enough. And that means the next period should focus on reliability. Stop the product work, invest. And this is how, if you are implementing this kind of methodology, that means you will have a feedback loop that is effective at keeping a certain reliability level, hopefully. At least it's a better shot than just going by the number of incidents that you have or the number of support week tickets that you got. All right, this part's actually something new. It's about alerting. And instead of managing, we are now like in a more tactical domain. And it turns out that SLOs also have to say something about alerting, which maybe is a little bit surprising because like alerting is fundamentally tactical, and we just saw like, well, we actually are targeting more the managerial time horizons. And the reason why it's useful for alerting is primarily because it focuses on user pain or symptoms that users are experiencing. So it really measures like, is the user experience bad? Versus stuff like, are my systems healthy? So a famous anti-pattern is kind of to alert on high CPU or low memory. That is something that actually is not of interest for the users, and it's something that your runtime or Kubernetes scheduling orchestration system should be able to take care of by itself. So if you are looking for like a high quality signal to alert on, then starting with your SLIs, the search for those conditions, starting at the SLIs actually makes sense. The thing it will not give you is kind of getting predictive alerts. So you're only able to see a degradation of the SLI once the user experience is degraded. Sometimes you want to just prevent the degradation by renewing your certs in time or by like buying larger disks. So it's a great starting point for alerting, but it's probably not the end point. You will need some complementary alerts for some things. Now, if you start looking into SLIs and SLOs for alerting, you will kind of need to understand how the SLI is moving first. So that's kind of the first thing you have to understand. So maybe you're thinking, yeah, okay, until the SLO is, the error budget is depleted, that we are like waiting too long. Let's just say the error budget was like going down by a small percentage over a time period, and alert on that. So that's quite close to what we want to do, but we have to like become aware of the subtlety. So essentially, if we are like advancing this 4-week time period by 1 minute here, we have 2 areas that we have to worry about. So we are seeing new stuff that just came in, but also like other stuff goes out of sight that happened exactly 4 weeks ago. So if the error budget actually goes up, it can mean that good things happened here, or just that bad things went out of sight. And conversely, if the error budget goes down, it can mean that bad things happened here, or good things went out of sight. And you have to be able to differentiate between the 2 of those if you want good alerting rules, because for alerting you care about this stuff. So we need now a like little bit of a different measure that is telling us like how the good events, or this kind of like the things that happened right now, is comparing to this longer time frame. And here we come again to a point where there are like different versions, and we'll see this in a little bit. But my take is that burn rate is the right concept to look at that. And this is actually also the context where burn rates arise in the literature. But I would say burn rates are fundamentally about measuring like how the new things that just happened, like maybe a minute or an hour ago, are comparing to like the longer time horizon and the SLOs and the error budget that we have set for that. We again calibrate the scale in a similar way that we calibrated the error budget. This time burn rate 0 means no bad event, And burn rate 1 means this behavior inside this region A is exactly acceptable, so exactly at the SLO level. And if you sustain that behavior for a longer time period, then we would, like for the SLO period, we would exactly burn out the error rate. Exactly, so error budget. Okay, so there's a very simple way to do it, which is not naive burn rate, which like I've seen basically everybody doing it this way. And there's a like different way, which I found more natural, but yeah, we'll get to that in a bit. So here the idea is like very simple. We just compare the current error rate to the SLO. So say we had 10% errors over the past minute. So this is implicitly over the minute. And then we look at the SLO. So let's say the SLO was 99%. So 1 minus SLO is 1%. So we have 10% over 1%. Then we have a naive burn rate of 10, which just means, yeah, you are burning your error budget 10 times faster than than you should, or it's allowed for you to do. So that first measure like is exclusively focusing on the last minute. So that's something to highlight. We are just looking at the behavior over 1 minute and then kind of make a statement about like how fast we are burning the errors. And again, the problem arises if we think about like the total requests, how widely they differ over the time period. And I think what we need to do in order to get a better grasp on burn rate is really look at these longer time periods. And like here's a fairly natural like way to do that. So instead of looking error rates and comparing them to the SLO, we look at just the absolute counts. So we basically look at the bad events we got in the last minute, and then we look at the error budget that we have, like the total requests, then multiply it with 1 minus SLOs to get like the total absolute allowable errors over a longer time period, and then we divide it down by this kind of number of minutes in a week, and this kind of gives us an absolute error budget for each minute. So we count the total bad events, so total failures, by like the total number of allowable bad events that we have, like basically on average for every minute in a 4-week period. And if you work out the math, then this is exactly what it is. And now if you go back to the book and look at the alerting rules, then this is kind of the best practice that is recommended. So we want to page if 2% of the error budget is consumed in 1 hour, and then have like multiple of this kind of burn rate conditions, and they are called burnout conditions. And turns out you can translate this kind of condition very naturally in a condition on the total burn rate. So if we really take this literally and do the calculation, then this will be equivalent to saying like a 1 hour total burn rate is larger than here 2% times a constant number of hours in 4 weeks. And then if you do the math, it's like 13.4. And yeah, so basically this condition is a threshold on the total burn rate. And if you want to put that in your monitoring system and actually alert on it, then the way you can do it is just like look at the total errors over the past hour. That's something that you should readily have available as a metric, or maybe some over like a small time period. Then you have this constant, which is 13.4 times 1 minus SLO, and you know that up front. And then you have this 4-week average events per hour. And here we come back to this observation that we had like a while back, that the total events over 4 weeks is actually something that is moving extremely slowly. So probably you could get away with just inserting a constant here. You can definitely get away with like updating this alerting rule with a cron job every day. So usually this 4-week averages, they are really barely moving at all. And there's no like meaningful like contribution on an hourly basis to this alerting rule coming from the variance here. Now, if your request rate is constant, which is kind of a big assumption, right? Usually at night you have a lot less events, but if it's constant, then the naive burn rate is actually the same as the total burn rate that I introduced before. So it also means I can like use the same condition here and get the same alerting rule under this condition. And if you plug it in, I can slightly simplify it. So here again, you're looking at an error rate over a past hour, so something you have readily available as a metric, and then you are comparing it to a constant. And this is the version that I have seen in the books, and I also like have seen in implementations being used. So basically just have a condition on like a rate that only takes into account like things that you see on a 1 hour basis. It doesn't compare actually to a longer time frame. So if you are like putting this on graphs, this is how it looks like. So I have put it like both burn rates as 2 graphs down here. So the naive burn rate, again, it's just like dividing the error rate by 1 minus the SLO. And if you remember, both of these outages had the same error rate. So also the naive burn rate, in this case, it's the same. So here it sits at the value 50. One thing to note is that this kind of scale is broken into 2 areas. So at 10, it kind of moves to a much like lower zoom level, if you like, because we do want to be able to see something that is close to 1 or close to 0. And we also want to be able to see something which is further high up, but it's kind of important to keep that in mind when comparing the relative size of those like spikes. So again, here naive burn rate is at 50. Here it's absolutely the same. If you look at like what a burn rate should mean naively, then it was like, okay, we are burning stuff exactly as fast so that we are like depleting the error budget within the SLO period. And you see here that we're having very different slopes. So in both cases we had the same value, but this is kind of, it can take a few like days until we deplete the SLO at this burn rate. And here it's like very fast, so it goes down like immediately. And this is not reflected in the naive burn rate, so those are identical here, although those slopes are very different. And if we do the total burn rate, we see actually now the difference. Here it will be around 10, which is also consistent with the slope that we are seeing here. It's roughly 1/10 of the time we need to deplete the error budget completely, 1/10 of the SLO period. And here we are at 120, so it's well above 50, which is corresponding to the fact that the slope is extremely steep. So yeah, both variants have their merits, and have a different behavior. And you can use both of them for alerts. Again, we have seen how the alerting rules are looking like. And in this case, if you alert on the total burn rate over 13, so here the red line is representing the threshold of 13, you will not be paged. In this case, you will be paged in that case. And if we use the naive burn rate, then in both cases we are above 13. So we'll be at 50, and then we will get an alert firing in both cases. And yeah, depending on what you want, you may want to choose one over the other. That concludes the talk for today. Here are like my 4 takeaways. I just want to repeat here on the last slide. So the success of any SLO program fundamentally, I believe, is measured in your ability to steer reliability decisions. So it's fundamentally about management. If you're able to present SLOs to your management and use it to gauge what you should do next week, then I think it's a big success. Error budgets are like just the same thing as SLIs, just look at it as at a different scale. Burn rates are about stuff that happens right now, and you can use them for alerting. And finally, you can actually use SLOs for alerting as well if you are using the proper math and looking at the right burn rates. Thank you very much for attention. All the best, and I hope to see you soon. Bye-bye.